Okay, so hello everyone. Welcome to the seminar of our course. Today we have Professor Fernando Quevedo. He is, apart from being my favorite personality and probably one of my favorite physicists out there, he is a leading string theorist and he did his PhD with Steven Weinberg and has various influential papers. Apart from that, he has interesting notes and taught interesting courses like standard model and supersymmetry, which are out there and which are excellent resources for everyone. He also served as the director of ICTP and worked for the development of physics and science uh, in for developing countries. So we are very glad, and I'm very glad and honored to have him here today. Over to Professor Fernando.
Oh, thank you very much, Ahmed. Thank you for such a kind introduction. So it's a pleasure to be here and communicating with all of you. First of all, before starting, I would like to wish you the best with all these events that have been happening at Bangladesh, and I hope things will go for the best. And if I could be of any help, I'm sure is not that much, but if I could be of any help on anything, let me know. And yes, and also want to congratulate Ahmed and Iqbal and everybody who has been involved in these courses, because I think this is a great initiative. And I'm a big fan of this Physics Without Frontiers program, and I'm glad that this is incorporated into that program that I think it has a lot to offer and has done a lot of good things. Yes. Only last week I was in the graduation ceremony of 38 students from Afghanistan who went to Iran to get a master's funded by this program, which I found very, 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 very good. So anyway, well, the title was chosen by Ahmed, so I have to say. So he asked me to talk about from the standard model to string theory. It is extremely broad, and I will try to cover the main points, at least to give a general flavor of how things are. But I think it's impossible to cover things in the proper way in 1 hour, but I try to do my best. And some recommended reading, some between string theory and particle physics, because most of the string theory community are not just working on this aspect of getting particle physics from string theory, but they are approaching other general questions like the black holes issues and so on. And so in that sense, the book that is available that is about relations with the standard model and something that can be eventually observable is this book by Bañez and Uranga, which I found quite good. And in more recent lecture notes from Arthur Hebecker that are available online. There are also more specific ones by Kumru Rafa and company, string landscape ensemble, which I think is quite good. And then we have several reviews. One review on string cosmology in general that we wrote with Michele Ciccolo, John Conan, Ansho Maharan, and Susha Parameswaran, and Yvonne Zavala last year. And then a review that I wrote also last year with Leanne McAllister on one of the important subjects of string theory, which is model stabilization. And I will touch on it a little bit today. And as Ahmed said, we just uploaded this Cambridge lectures on the standard model that just came out this week, I think, with my former student Andreas Schachner. So for the first part of my talk, I think this is the reference I've been using. Okay, so I start my lectures on the standard model and in general with this general phrase from Weinberg, which I think is the way to try to address these questions about the standard model, which is that the purpose in theoretical physics is not to describe the world as we find it, but to explain in terms of a few fundamental principles why the world is the way it is. So for me, the key words is explain and a few fundamental principles. So you have to reduce the basis of our understanding to the few number of principles, and from that explain what we observe. So that's, and for that we use the fundamental theories, which is special relativity and quantum mechanics. So still after 1 century, they're still the two fundamental theories that we have. Some people usually say general relativity is more general, but I disagree, because special relativity is general, and general relativity only applies to one interaction, which is gravitation. And so in that sense, I think these are the basic theories that we have, and we have to use them to see what kind of implications we can extract for the real world. And saying special relativity means that we have to use the algebra of the symmetries of the special relativity, which is the Poincare symmetry. And the Poincare algebra is, you have generators, the momenta, p mu, and the n mu nu, which includes boosts and rotations. Okay, so the p's commute with themselves, but then they transform on the rotation of boosts in this way, and then the rotations transform also by having these non-trivial commutators. Okay, so that is the special relativity part. The quantum mechanics part is to find representations of this algebra on quantum mechanical states. And that's what Wigner did in 1939. And he did a very systematic way of classifying the representations of this Poincare group. And we can see it, for instance, for massive particles. He found the operators, or I'm sorry, generators that commute with every combination of the generators that commute with all of them. These are called the Casimir operators, and they can, since they commute, they can be diagonalized simultaneously, and that gives us the quantum numbers, the mass and the overall spin. And then for a given mass and spin, we have the momenta which commute with them, because the p mu commute with themselves. And then for fixed momentum, they can be in 4 dimensions. You can have, this will correspond, say, to a massive particle. We can go to the rest frame and pick the mass, and then you have 0, 0, 0 in the spatial dimensions, and this is the time dimension. And then you see what are the generators left that leave this invariant, and those are the rotations. So that means that they justify classifying the states by mass, or overall spin, momenta, and spin, and a third component of the spin. Sorry, my voice. And so essentially, in one multiple, we have, so if we go from minus j to j, it goes to 2j plus 1 elements, and those are the states of the particle. So in this case, for j equals to 1/2, we have two states. 2j plus 1 is 2. And then there will be the two states of fermion, say, an electron. For j equals to 1, you have 3 states. Those are the 3 states of a massive vector field, and so on. But this also implies the possibility you can have p squared not only equals to m squared, but also to minus m squared, and that will be tachyons, and that some particles that we haven't seen, because they will say they will move with faster than light, but we know more or less how to understand these particles, in the sense that you think about potential for a particle. So being the vacuum means that you are on top of the maximum of the potential, not on the minimum, and so you're on the wrong vacuum. Sorry, and then you have to go to the minimum to do your proper physics, and to span around the minimum. But still, we have to put a question mark here that the vacuums can create some instabilities, essentially, and that's why we put the question mark. Then the massless particles are probably the most interesting ones, because we organize our knowledge by energy, and the lowest possible energy are the massless particles. And in this case, the momenta, you cannot go to the center of mass, because the particles move with the speed of light. So this is the best we can do, to have energy here, energy there. So the p mu equal to 0, that would be the mass. And then it will look like something that will leave invariant this state will be in SO2 rotation. In the same way that here there was an SO3, there will be an SO2. But that actually is wrong. And there's a bigger group that lives invariant these states, and it's called the Euclidean group in 2 dimensions. And that group is complicated because it has an infinite dimensional representations called continuous spin representations, which have not been observed in nature. So we have here the first implication of special relativity in quantum mechanics, where first of all you have tachyons. You may have tachyons that we don't see, but also you have this infinite number of states that we don't see neither. And that would be problematic. Wigner eliminated them because he said that will create infinite heat capacity or so to excite them, and so it would be unrealistic. And Weinberg, in his book, he said, well, we haven't seen them, so let's forget about them. And so I insist that this is a question mark. We have to explain that. And when we forget about them, we just restrict to the SO2 group, the rotations in 2 dimensions, and then we get the states being classified by momenta and helicity. So we don't have the first two numbers here because the mass is 0, and we don't have the spin, we just have the helicity that can be plus or minus half an integer. And so helicity 0 will be the equivalent of a spin 0 for a massive particle, but for a massless particle. Helicity 1/2, the same thing, plus or minus 1/2. And both helicity plus or minus 1, there are only 2 states. Whereas here, for a massive particle, there will be 3 states for j equals to 1. So that's a fundamental difference between the massless and the massive. And that's one of the things that I hope you have been taught in the last few weeks about the Higgs mechanism and so on. And so for spins 0, 1/2, and 1, we want to describe interactions, and the interactions are described by quantum field theories that I understand you have been learning in the last few weeks. And for you go beyond 1, you have to say 3/2 and 2, you need gravity. 2 will be the particle of gravity, the graviton. And 3/2 will be a particle that we haven't seen. It's called the gravitino, that can be only coupled in a consistent way only through gravity. And that we haven't seen either. But to describe interactions for these particles, we need what is called effective field theories. And I will say a few words now about effective field theories, which is the way we understand physics now is through effective field theories. Please interrupt me at any time you have any questions. So, but these are general statements about quantum field theories or gravities. And if you just try to describe a general quantum field theory, you can try to say, oh, what are the predictions of quantum field theory that I can test experimentally? And there are very few. One is that identical particles. The difference is that all the electrons are equal to each other. So you can replace an electron and an atom by another electron. It will be the same atom essentially. And that's something that quantum field theory can tell you, because the electrons will be excitations of the electron field, which they are all the same. Antiparticles, so for every particle you need an antiparticle, and that's also a general implication of quantum field theory. And of course they have been seen because for the electron you have the positron and so on. The CPT theorem, this is changing particle by antiparticle, parity, spatial parity, and time reversal. That's an exact symmetry. Each of them is not a symmetry in your interactions, but the combination of the 3 of them is a symmetry, and it's a general theorem that can be proved just by using quantum field theory. And also the relationship between spin and statistics, that the bosons can be all together in one single state, whereas fermions, they cannot be 2 fermions in the same state, and that's why we have the atoms being non-trivial. That's the general result. So integer spin, which are bosons, behave in one way, half integer spins, which are fermions, behave in another way. Yeah, the standard joke that we used to say that in a university, the students are fermions and the professors are, the students are bosons and the professors are fermions. But that's no longer true because we are losing our offices and also, so they should have to find another joke about this. And then there's this, the coupling, which is what I was telling you about effective field theories. Essentially, you can understand, you want to understand physics at a given scale, you can decouple from the higher scales and just concentrate on a quantum field theory at the scale that you're asking your question. That is a general thing. Okay. So, but the important thing that I want to say here is that, look, there are only 5 general predictions. There are very few. from quantum field theory, and the reason we believe that quantum field theories are correct is because we have concrete models which are realized as quantum field theories, which is the standard model. And the standard model of particle physics, I understand you have been attending lectures on this. So we have a symmetry, SU3 cross SU2 cross U1, that describe all the strong and electroweak interactions. And so the mediators of those interactions are gauge fields, which are the gluons for SU3, W's and Z's, and then at the end, the photon for the SU2 cross U1 once is broken. And then you have the matter particles. So and these are all the mediators are spin 1. The matter particles, quarks and leptons, spin 1/2. They all start with helicity 1/2 and then being massless, and they get a mass because of the Higgs mechanism. And then we have the Higgs, which has spin or 0, and that was just recently discovered only 12 years ago or so. And then there's also gravity. We cannot forget about gravity. And gravity is described by a particle of spin 2, which is massless as the graviton. And we put a star here because, of course, we haven't seen the graviton, but we know why we haven't seen it, because it couples extremely weak. And but it fits with the general picture I was telling you before, that we have these particles can be spin 0, 1/2, 1, and 2. We are missing the 3 halves that I will say something later. And that's the general result of what we describe in using relativity and quantum mechanics together. And the standard model is a particular case of that. Okay. So this is the Higgs potential, and this is the bump that gave rise to the Higgs, and it's a great triumph of quantum field theories, and a great triumph of what people call gauge field theories, and effective field theory, in the sense that we can just understand this at the scales which are of the order of 10 to the 3 GeV, which is 1,000 times the mass of the proton, which is the energy that we can observe now in the biggest colliders at CERN. Okay. So, that's the standard model 1. So I say it's a compelling structure because the gauge theories, essentially, they're unique in the sense that you have to have either, if the gauge fields, the spin 1 fields, either not interact with themselves or interact with themselves. If interact with themselves, they're called Yang-Mills theories. If don't interact, there are a billion U1 theories. And we know how to describe them. And the photon is a particular case of the ones who are not self-interacting. And the gluons and the W and Z are a particular case of the other ones. So that's what they're described by Yang-Mills theories. There's the Higgs mechanism. That's the way to give them a mass, and gives a mass to all the quarks and the leptons. And then there's one and only one helicity 2 particle, which is the graviton, massless. And there are no more for helicity higher than 2. It's a general theorem that was proven by Weinberg in the 1960s in a beautiful paper. And so essentially, you can prove in general that there are no interacting spin bigger than 2 massless states. And that's precisely what we have seen in nature, which is good. And the only freedom we have essentially is the choice of the gauge groups, the choice of the symmetry SU3, SU2, U1, but it can be any other group. The representations of the matter fields, because in the standard model, the fermions, so the quarks and the leptons are essentially in the fundamental representation of the corresponding group, but the groups have many other representations of different dimensionality. And they will have to also choose the couplings, how they choose with each other, Yukawa couplings and so on. I keep insisting that we are still missing the spin 3 halves. I have to say, well, another one that we're missing is this. We have the Higgs, which is spin 0, but there can be also what people call is another scalar particles, which are pseudo-scalars, and they have not seen, which are not divided under parity. And an example of that we will mention later on, which is the axion. Okay, so the important thing is that the standard model can be seen as an effective field theory. And an effective field theory means the following. So take the simplest case, a scalar field that you have seen. And we can write a Lagrangian, which is d phi minus a mass term, then a cubic coupling, then a quartic coupling. And just always stop here. And we stop here for no particular reason, because we can continue phi to the phi to the fifth, and phi to the sixth, and so on. And so that's the most general Lagrangian we can write for one single field. The difference that the first few up to lambda phi to the 4, they're called renormalizable, and the rest are non-renormalizable. For a long time, people thought that non-renormalizable theories were sick and you couldn't deal with them. And the questions, we have to concentrate only on renormalizable theories. But that's a mistake. So that's why we have to insist that these are, Weinberg used to say that non-renormalizable theories are as renormalizable theories. So there's nothing wrong with them, except that we cannot trust them up to the higher scales. And that's the scale lambda that's playing the role here. So if we do physics at scale much smaller than lambda, these terms are suppressed because they're suppressed by powers of lambda. And so you can neglect them. And that's how we can deal only with the renormalizable terms. And that's how the standard model is described. But if you want to explore higher and higher energies, we can consider the effect of this one. If you want more precision, we can see, well, what is the effect of this term? We can still neglect that one because this one is smaller than that one, and then get to the precision where this one is important. And then we want a little bit more precision, we can include this one. And we want a little bit more precision, we include the next one, and so on. And all the way to infinite number of terms. Actually, the Einstein theory is one of those. You write the Einstein Lagrangian, which is the Planck scale times the scalar curvature term, which is the Einstein-Hilbert axiom. You can expand the metric into the flat metric plus a perturbation h, which is the physical object, and then you can get an expansion like that, dh squared plus dh squared times h divided by m Planck plus dh squared h squared over m Planck squared, and so on, where m Planck is the 10 to the 19 GeV or so is the combination of h bar, c, and g, and the fundamental scale of quantum gravity. Okay, so essentially, there's nothing wrong with gravity as we know it, because it's only it's a non-renormalizable theory. You can expand on powers of 1 over n Planck, but it cannot be. We cannot trust it at arbitrary high energies, because then at arbitrary high energies we have to consider the infinite number of terms, and then we are unable to describe that. So, and the standard model itself, as I say, is an effective field theory. The Lagrangian will be the standard model Lagrangian that we described, that has been tested beautifully. But then you can add a term which is this is dimension 4. You can add a dimension 5 term divided by mass, dimension 6 by m squared, and start making predictions about what is the relevant part of that part. And that is called the standard model effective field theory. And that's how people are trying to extract information of what can be beyond the standard model by just writing in this way. This was extremely simple, but for some reason, the community took many years for the community to adapt this way of thinking, which I think is the correct one. And of course, in general, then the standard model and gravity are effective theories. You can have the standard model just coupled to gravity with a non-trivial metric, and then do the expansion. Notice that I put here the Einstein-Hilbert action only comes here as a third term. The first term is just the standard model Lagrangian. Then there is no derivative terms, which is called lambda. Then the m Planck squared r, which is all the things that I have here, which are all the derivative in terms of age. Okay, so this term is called the cosmological constant. It's the leading order in the derivative expansion, and I will say more about it later on. So all this is okay, but there are problems, and I will address them later on. But before moving there, I want to say that there is another standard model, which is a standard model of cosmology, and it's called the lambda CDM. The lambda is that same lambda that I mentioned there, the cosmological constant. This is Einstein's equations. And CDM stands for cold dark matter. And the impressive thing about this is that this satisfies all the experimental tests that have been made in regarding cosmology in the expansion of the universe. And this lambda is zero for Minkowski spacetime, but if it is positive, it's called de Sitter. And if it is negative, it's called anti-de Sitter, and that tells you how curved is the space. And the impressive thing is that is observationally, lambda, if or any variation of it, is of the order of 10 to the minus 120 in units of the M-Planck. So this is a huge difference between M-Planck and this. This is imagine it's 120 zeros precision that you need to get, and that's how small this lambda is, or representing in the Einstein's equation. That is one of the mysteries we have so far, and I will say more things later on.
There is a question in the chat.
Okay,
Uh,
please.
so it says, so the motivation of doing effective field theory is only dealing with spin phi half or spin 2 particles, or there are more reasons behind that?
Oh, yes, it's for all of them. It's for every single spin. We can just effective field theory is the general thing to do. Just to write the most general thing consistent with every symmetry you have. And you can have the scalars, the fermions, and engaged fields, everything. So that's why the standard model can be generalized by just adding these extra terms. And the way we say that what people call the standard model was the first term in that expansion. Then the 1 over lambdas and so comes from higher, and that includes all the fields of the standard model. And the reason these terms have not played much of a role so far in physics is because we don't have enough precision to see what they can be useful for. And actually, of the observations we know, tell us how big the scale at which we can trust is, this capital. So let me just go back. I don't want to confuse you. This lambda here has nothing to do with the lambda, the cosmological constant here. I apologize for the use of the same letter. And so the fact that the standard model, for instance, here, these terms are not I mean the standard model Lagrangian has been tested very well with observations and it fits very well, tells us how large this fundamental scale is, such that these terms are negligible. And for instance, for neutrino masses, this scale has to be 10 to the 14 GeV. For proton to be almost stable as we know it, the scale has to be close to 10 to the 16 GeV, and so on. So that gives information of where is the scale you have to go to find the new physics. And but it covers every single particle. Yes, thank you for the question. Okay, and so and then I won't go into the test of cosmology because it will be too much. So, but then the whole history of the universe can be explained so far with the knowledge we have the standard model and with this lambda CDM picture of cosmology. However, we want to make the point, and that's another motivation for string theory. And in every single thing I mention, I will always try to find something that is still missing. And this is the thing is missing, that contrary to the standard model of particle physics, where we have a well-defined theory, which is the gauge theory by symmetry crosses to measure one, where you can do all the calculations and so on. For cosmology, it's only a prescription. You have lambda, cosmological constant, and cold dark matter, and then the standard model, of course. And then from there, you can compare with experiments. But the lambda is put in by hand, and the cold dark matter is put in by hand. So there's no theory behind. So that's what cosmology is more challenging than particle physics somehow. And then these are the open questions that I mentioned before. So this is very successful, but we don't understand gravity at the fundamental level. At some point, we want to understand it at all scales. And for that, we need the theory of gravity, not only an effective field theory, but it's just a full ultraviolet complete theory. And we don't have it. So that's the main problem in physics. In cosmology, we need to explain the covariant acceleration, that's factor lambda, what is dark matter, the baryogenesis, sorry, I misspelled, why we're made out of particles and antiparticles, and so on. The why questions, why we live in 3+1 dimensions, that's a question. And so why there are 3 families of quarks and leptons and not only one? Why there are 3 gauge interactions plus 1 gravity? There could have been many other ones, but This is what we have. And the standard model has many free parameters, more than 20, that we don't have any explanation. And then there are the questions that have been guiding our research the last many years to go beyond the standard models. And these are the hierarchy questions. And as I said, we write the Lagrangian as an effective field theory with the coefficients and operators of the different dimensions. So this coefficient would be the 1 over lambda that I was mentioning before, all the way summing over all of them. But the dominant one, the operator of dimension 0, that's the cosmological constant. So that's the most important term in the Lagrangian, and we don't have an explanation. So why this lambda is so small and it's almost 0? We have been neglecting it since Einstein's times until now. Actually, Einstein introduced it and then took it out because he thought it was a big mistake. Actually, his mistake was to take it out. It is the dominant term in his equations. And why it's so small is a big challenge. But the challenge is not just to explain a number and that's it. The challenge is that there will be corrections. Everything, a single thing in the standard model contributes to the vacuum energy. Just the electron itself and the Higgs itself contributes to vacuum energy to many orders of magnitude. So in that sense, with all the physics we know, lambda should be much bigger. And that's a challenge. And we cannot just fix it because every single correction from all the standard model will again make it bigger. So this quantum gravity I mentioned was the most important problem of physics. Explaining this is the most important puzzle, the biggest puzzle we have. It's not that fundamental as the describing gravity, but just to explain why this is so small. Then there's operator of dimension 2. That would be like the mass of the Higgs. This has dimension 2 because the scalar has dimension 1. So H squared has dimension 2. So the coefficient has dimension 2 also. And that's also problematic because this is a diagram that gives a correction to the Higgs mass. So this is a Higgs, this is the Higgs, and you have in the loop any particles from the standard model. And again, they will give a correction to the Higgs mass, will make it as big as you can, as big as the cutoff of your theory is. And then you have to explain, if you go all the way to the Planck scale, why the mass of the Higgs divided by m Planck is the order of 10 to the minus 15. It's again a dimensionless number that is extremely small and we don't have any explanation. And again, loop corrections give you a correction to this number. And then there's another one called the strong CP problem. That usually you have the gauge interaction. You have the gauge field times epsilon times the gauge field. The coefficient is called theta, and the observable part is called theta bar. It has to be smaller than 10 to the minus 10 observational, and we don't have any explanation for that. So these are concrete open questions that we have to address from the standard model. Okay, so that's and many of us have been spending a lot of time trying to address these questions because this is we thought or we think that they are basic questions for the standard model. So we need to go beyond the standard model and we have two approaches, the top-down and bottom-up, the main one approaches. Top-down and say, well, let's try to find a theory of quantum gravity. And that's where the string theory will come in. But there are others, asymptotic safety and others, loop quantum gravity, and so other people try to address. I have to say, emphasize string theory because that's the only one. It's not only theory of quantum gravity we need, but we need a quantum gravity with all the other interactions together. And the string theory is, as I said, the one that addresses all of them. Then there's an idea of supersymmetry that can generalize the basic symmetries we have from the Poincare algebra that we had to include fermionic operators, generators, I'm sorry. You have grand unification and others. And the bottom up, as I told you before, you have the standard models and effective theory start exploring each of the corrections or introduce extra particles to address one of the questions we have and so on. So let me say a few words about supersymmetry. Supersymmetry, I told you we had the M mu and the P mu as the generators of the Poincare algebra. There's only one general extension of the Poincare algebra is to introduce operators or generators, sorry, that are themselves fermionic, like the psi, the electron field is a fermion, so there can be and here the momentum is a vector, n mu is a tensor. So why not having operators which are spinors, spinorial, and that has been proven in general that that's the most the only generalization of the Poincare algebra as a space-time symmetry. And thus you have here the commutators. And these are the anti-commutators because they are fermions. So you have two of these Qs give you a P. So that's interesting because that means that you take a fermion, Q, since it is a fermion times a fermion give you a boson. And boson times a fermion give you a fermion, but you have two times Q and Q bar acting on a boson, give you again another boson. But it's translated. It's translated because the product give you P mu, and P mu is the generational translations. So it's a real space-time symmetry. And the beauty of this is that it has natural predictions, like you have helicity 0, the scalar, like the quarks, leptons. Those are the, sorry, you start with helicity 1/2, which are the quarks, the leptons, and they will give you a partner, a supersymmetric partner, which is a boson. The lepton has another boson. For the photon, you have another, which is a boson, you have a fermion. For the gluon, you have a gluino, and so on. For the graviton, you have the gravitino partners. And the beauty of supersymmetry, it addresses several things. For instance, you have the corrections to the Higgs mass that I told you that was the source of the hierarchy problem. Now, if in the loop you have fermions, you add the same loop, but now bosons going around, and they cancel beautifully because of the supersymmetry. So in that sense, the hierarchy problem, this is about the source of generating a big mass for the Higgs. Now, if supersymmetry were exact, there would be no corrections at all. Well, we know the supersymmetry cannot be exact because with these particles we haven't seen. We haven't seen the scalar partners of the quarks or the fermion partners of the photons and so on. So that means that the symmetry has to be broken. Well, we know about broken symmetries because we know the Higgs mechanism, for instance, precisely about Higgs broken symmetries. So supersymmetry cannot be an exact symmetry of nature, but it can be broken. And by the, if it is broken at the scale of the standard model scale, so then that will explain the hierarchy problem, and that's why people were looking for supersymmetry for many years. Unfortunately, SUSY has not been discovered so far, so that's an open question. And then maybe this may have been the wrong direction. We don't know. So the hope is that it would be discovered in the next round of experiments, but we have to be totally open-minded.
There is a question. Okay, there are a few questions in the chat. Do you want to take it now, or let's say at the end of?
Yes, whenever you want. Yes.
No, up to you. Should I ask them now?
That was okay because then people will forget. And then, yeah.
Okay. Can you give a brief explanation of asymptotic safety in
Oh, very
quantum
good.
gravity context?
Yeah, that's nice. Asymptotic safety is a nice story. Is that we know that there is asymptotic freedom, which is the you know they have usually this running of couplings in general, and asymptotic freedom means that you have a coupling for the strong interaction that's very strong, and then it runs and runs, and at some point it get weaker, and goes towards a free theory. And so that's asymptotic freedom. And that, oh, actually it is here, isn't it? So it is here. So this is for instance, this is the strong interactions. You start with a strong coupling, and then with energies it gets smaller and smaller and smaller, so you get weak couplings. And whereas for the photon, for the electromagnetism, it's the other way around. You start with weak and start getting to higher and higher couplings, and at some point you will get to what people call the Landau pole, which is very, very going to infinity, the coupling. But locally, it's at the energy that is far beyond the Planck scale, so we won't see it. Asymptotic safety, that in this picture we have these three couplings that refers to the strong, weak, and electromagnetic interactions, but gravity is not included here. Gravity being non-normalizable, the coupling is proportional to the Planck scale. So it runs with energies. So this running is logarithmic. In the running of gravity is quadratic, is a power. And gravity starts almost zero here because the weakest interaction, and then can start going up. And at some point, this idea of asymptotic safety is that at some point, gravity will catch up with all of this, and then you will get what is called a fixed point. So it will be fixed point means that it will stop running. So it will be essentially what people call a conformal field theory. And then that means that you can that's it. You can describe gravity at that scale, and it will be a theory well defined. So even though the theory is perturbatively non-renormalized cell that we cannot trust the calculations. But when you go there, you go to the fixed point. Essentially, it behaves like a weak coupling theory, and then that's it. You wouldn't have to do. That means that gravity, as we know it, can be a consistent theory. And that was an idea that Weinberg came out with, as usual, because he was invited for a centennial Einstein centennial celebration in some point in the 80s or so. And he said, "Well, but what do I have? What can I say which is original?" And since it was about Einstein, it had to be about gravity. So he came up with that idea. And it so happened that now it's a very popular idea. I mean, there are whole communities trying to explore that, do the calculations properly, compare with how the standard model run and so on. And it's an open question. It can be a very simple alternative to string theory, but of course it doesn't address fundamental, more fundamental questions. But you want to address quantum gravity, that could be a solution. And so Weinberg still say it's a long shot, and he prefers, of course, string theory. It's richer and it can explain things. It has more potential to explain things, but you have to be open-minded, and that's a possibility. Yeah. Other questions?
There was another question regarding the cold dark matter. What you meant by cold?
Very good. Yes, cold well is the opposite to hot, and hot is like the neutrinos. Neutrinos will be hot dark matter because neutrinos are neutral, and so they don't interact with electromagnetism or with strong interactions, only weakly. And so that means that they will be a perfect candidate for dark matter. But since they're very light, they move very fast, and so they will be hot. And so that's that what cold will be a heavier particle or essentially a heavier particle, like neutralinos or something, particles which are 10 to the 3 GeV or so. So in that sense that they are not relativistic. So yes, and then there's this an exception with the axion that I may mention, that it behaves like cold dark matter because of the way that it fluctuates around the minimum of the potential. But that's what essentially cold means, not relativistic. So it's not a very light particle.
Yeah, I think you answered the next question as well, which is, do we always consider non-relativistic matter as cold matter, cold dark
Okay,
matter?
very good. Yeah, very good. Very good. Okay, so so I mentioned that about supersymmetry, and I will mention grand unification. Grand unification is an old idea, which doesn't solve that many problems, but it's very nice. In the sense that we know that the standard model, you have SU3 equals to cross U1 broken to SU3 cross U1. So there's an idea, oh, there may be bigger symmetries when higher energies with a gauge group which is bigger than SU3 cross 2 cross U1. So SU5, SO10, E6, or SU4 cross S2 cross SU2, which is the original Patel model and so on. And so there's breaking will be at very high energies, and then at the lower energies we can have that. So the standard model energy is 10 to the 2, 10 to the 3 GeV, and the God scale can be 10 to the 17 GeV or so. That was another idea, but there was a beautiful paper of Georgi Quinn and Weinberg in the 70s that said, well, this is a nice thing, but we look at the couplings. They say, well, this group is one simple group, like SU5 or SO10, there's only one gauge coupling. So what should happen is something like this, that you start with all the three interactions. They're very different at the scales that we see now, but when they run at higher energies, at some point there will be a point very high energy where they meet, and there will be there will be one single interaction. So that's a beautiful concept, because it's about all the interactions that we know will be different manifestations of one single interaction, one single coupling, that at some point the symmetry is broken and then they start evolving differently, going to lower energies. And remember, you can put this in the concept of cosmology. So this will be early universe, and this is late universe. So the early universe is higher energy, and then we are at a late universe like now. So now we see all the couplings being different, but in the early universe they may have been all together, all unified. So and actually the interesting thing about this, besides the beauty, is that the experiments in the 1990s, LEP in particular, they found evidence of see how these couplings are running, and you put see how they're running with the scale, because now they have enough information to see how they change the scale. uh, they will, you extrapolate with the standard model particles, they will go and meet precisely at one single point. It's totally, the generic thing is that they just cross each other like here. But it happened only you have supersymmetry. So that was a beautiful thing. So the experimentalists got crazy, and that's why we had so many experimentalists believing in supersymmetry for so many years. It was precisely because of this fact. You have from the low energy experiments a hint that you add supersymmetry. That means you add the supersymmetric particles that I mentioned in the previous slide. Then they meet at one single point, and that's a highly non-trivial result. And that's what people had expectation that at some point supersymmetry would be manifested. And it still may be the case that supersymmetry will be manifested at higher energy so far than we have observed. Okay. But then, as I said, no supersymmetry, not grand unification addresses the fundamental problem of quantum gravity, which is just to quantize space-time itself. That's the way of the Einstein would have said. And that's why string theory enter into the game. And I think I've been going very slowly. So let me just go quickly through string theory. Essentially, we start with forget about field theory at the moment. Do what people call phase quantization. Take a relativistic, take a particle of mass m, and you can describe it by the action in the mass here times the line element ds, which is you have to use this dx mu with a parameter tau. So that's the standard thing that you see when you study calculus variations and so on. And then you can look for the equations, and the equation will have a free particle. You get x double dot equal to 0, and that's the motion of a free particle. If you couple the particle to electromagnetic interactions, for instance, you have not only the coupling here, but also the coupling to the corresponding electromagnetic field, mu. And then you take the variation of the field equation from the equation from here, you will get the force, the Coulomb force equation, or coupling of the particle to electromagnetic interactions, and Q will be the charge of the particle. And you can have the electric part and the magnetic part version of this coupling, and that's more or less what we can just describe a particle by itself. So strings is the same concept, but now in 2 dimensions. You have, instead of a point particle, you start with say in this case, closed strings, and let it develop in time. You have an action. It's called the Nambu go-to action, and you can describe the motion of the string. And instead of coupling to the gauge field, now since you have 2 dimensions here and of the string, because the point particle is only 0 dimension moving in time. Now we have a 1 dimensional moving in time, so it's 2 dimensions. And then it couples then to an object with 2 indices. Instead of a mu, we have a p mu. And that's a string. And of course, you can generalize this to higher dimensions, and you can couple the object to to an object with many indices. And those are the people called the brains, main brain or p brain in general. There's another way of writing this, and just formalism that people use is called the Polyakov action. It's written in a different way because you need to have the square root, but at the end it describes the same physics, and that's how people use the quantization. This is the way people describe the quantization of string theory. You have to choose boundary conditions. If it is a closed string, there's always periodic boundary conditions because you go around. But if it is an open string, you have to see what kind of boundary conditions you choose for the string, the 2 endpoints. And you can choose Neumann and Dirichlet boundary conditions as standard in differential equations. Neumann with the derivative is 0, and the Dirichlet with the position is not changed. And you have some of the directions, you have many dimensions, many of these x, which are the coordinates of the strings, and you can have any number of them. So some of them you can set them to Neumann, and some of them to the Dirichlet, and then you can have you have in p special dimensions and time choose the Neumann boundary conditions. Then in d minus p, where d is the total dimension, d minus p dimension, you can choose the Dirichlet. And then the endpoints of the strings, where in this case, when you choose the Dirichlet boundary conditions, is what people call d-branes, because these are spatial objects of dimensionality p, which are the d-branes, and that's where the endpoints of the open strings will be fixed. So you have the picture with closed strings and open strings, and ending up in deep brains. And as I say, the couplings of the deep brains of the brains have p dimensional, and then you have p plus 1 because of time, and it couples an object with p plus 1 indices. These objects are unique objects in higher dimensions. In dimensions 6 and on over, these are new objects, different from what we have been discussing in the 4 dimensions in terms of gauge fields and so on, because they have objects which are antisymmetric with many indices. In 4 dimensions, they are equivalent to gauge fields or to scalars, but up from dimension 6 and up, they are they have their own life, and they are important. Okay, I will skip this part, but you can prove by quantum consistency that the number of x, which are the number of coordinates, to be consistent, you have d equals to 26, and you include supersymmetry, you include fermionic components, d equals to 10, and that's the standard thing that people say is string theory lives in 26 or 10 dimensions. And you can compute the spectrum. In this case, the questions of motion are very simple. They're like wave equations, so you can do a mode expansion that people do like in a Fourier expansion, and then compute the Hamiltonian, which is the energy, and then from that you have creation and annihilation operators, identify a vacuum state, and apply creation and annihilation operators to that vacuum state, as people do in field theory. The interesting thing, the vacuum state, when you have the overall mass, give you a tachyonic in the bosonic string. That means that the mass square is negative. You can have this minus 2 plays a role. So then you have to add by creation operators to raise the level and to get the mass to be 0. So you need at least 2 of them. And you have 2 of them, you have 2 indices, and then that means a general object with 2 indices can be split into a symmetric part and a asymmetric part and a trace. And the symmetric part will be the metric, the space-time metric. And the symmetric part is the object that I've been telling you, coupling 2 strings. And the phi is called the dilaton. And those are always there. That was the case for open strings. For closed strings, I'm sorry. For open strings, you have again the vacuum is tachyonic, and then you need only one operator with one index to get a massless state, and that will give you the gauge fields, the electromagnetic field, or something like gluons and so on. So this is a way of string theory predicting the states we have seen in nature. So things like the metric of space-time, the gauge fields and so on, the scalar fields and so on. And in superstrings, when you have supersymmetry, the tachyons disappear from the spectrum. So you can explain why there are no tachyons, because when the supersymmetry is added, the tachyons are projected out. You don't have to do anything. They're just it's not there. And you start only with the massless states, and then all the massive states. Remember that you can apply an infinite numbers of these creation operators, so you have an infinite tower of massive states. But you skip the tachyon is projected out. And also this continuous spin representation that I told you in the first slide, that there were infinite numbers because of this representation of the Poincare group. In string theory, they are not there because they had an infinite dimensional representation, where in string theory, the massive states are related to the massless states by creation and annihilation operators. So if the massive states are finite dimensional, that means that the massless has to be also finite dimensional. So again, string theory can explain something that we have not observed, which is this continuous spin representation, infinite number of particles that nobody could explain. Now we can explain why they are not there. And which I think is good. If you don't mind, I can skip the slides just to try to finish on time. Can I go over a few more minutes?
Yeah, sure. You can go
So
10,
15 more
15 minutes more. Yeah.
Okay.
Sure.
Okay, thank you. So essentially, in the supersymmetric theories, string theory with supersymmetry, people have classified, and there are 5 of them with different numbers, which they all require 10 dimensions. They all have supersymmetry, some these Q generators that I told you, and they have the massless states. They have different. These ones have, as I told you, the symmetric tensor, which is a metric antisymmetric tensor, and the dilaton. Then you have also gauge fields with the index m. So that's perfect for having the standard model. And others have other more general antisymmetric tensors, CMNP and so on. Look, they all have the GMN. So that comes into claim that the string theory predicts gravity. So again, you don't put gravity by hand, gravity comes out, which is good. In these cases, you don't put gauge fields in, they're just consequences of the gauge fields and so on. So in that sense, that's how powerful the string theory is. But this prediction of 10 dimensions is not very realistic yet. So we have to do something with that. And you have to say that there is a cousin of all the string theories called M theory in 11 dimensions. That was beautiful. The people over the years using this concept that I told you before, that there are no particles with spin higher than 2, massless. You can find a dimension, the highest dimensionality of a supersymmetric theory because of that, and the highest dimensionality was 11 if the dimension is even odd, and 10 if the dimension is even. And precisely, string theory satisfies the dimension, the highest even dimension. And well, the highest odd dimension is a theory, supersymmetric theory, so of course, 11 dimensional supergravity, that people have found in the 1990s to be equivalent by some what's called duality to the different string theories. So they're all related to each other. Each of these theories, they're all related to each other by the symmetries called dualities, and they're also related to this M theory. So at the end, all of these 1, 2, 3, 4, 5, 6 apparent different theories, they all happen to be the same theory in different limits. And that's what you expect the fundamental theory to be fundamental. It has to be unique. And in the up to the 1990s, there were many. Now, after from the 1990s, and now we know that there is all these are manifestations of the same theory, which is very appealing also. But we had to reduce the number of dimensions, and we had to go to dimensions, to smaller dimensions. The simplest case is just to consider 10 dimensions go to 9, and the extra dimension is a circle. So we can see this. And this is the simplest case, and this is the case that Kaluza and Klein considered 1 century ago, without thinking about the string theory. Just so let's see what happens when you have an extra dimension. And then there, it's interesting that the way to describe the circle is that you have a coordinate, the 9th coordinate, to be periodic with period 2 pi r, where r is the radius of the circle. And then, if the coordinate is periodic, the corresponding momentum has to be quantized, because e to the ixp has to be 1 in the wave function. So the momentum is the sum of the right moving and left moving momentum. And so this is m. This m is an integer. And it has to be quantized in powers of 1 over r, so that momentum times x, the r has to cancel to give you an integer, 2 pi times an integer. So but on top of that, this object, there's what's called winding states. And the way to see it is that you have, imagine a closed string. You can see the cylinder here. This is a closed string going around this, and the cylinder is closed by itself, so there's no winding. But this one is a string going once on the cylinder. There's a winding string, and this is one going twice in the circle on the cylinder. And this the larger the circle is, the more energetic you need to be, and that's by its proportion to the radius. It's an integer times the radius. So now the mass formula is that I had before. Now I have to add the contribution from the momenta and the contribution from the winding. And so then you have states which are winding states and momenta states. And you have an infinite number of them. The momenta states, they're your proportional to 1 over r, 2 over r, 3 over r, and so on. And then you have on top of that the winding states, which are proportional to r. There's a nice formula here that if you look at this equation, you change r to 1 over 2r, it gives you the same equation. But if you also change the two integers, the winding and momenta. This is a fundamental symmetry in string theory called T-duality that tells you something very deep. That changing r to 1 over r means that you're changing small distances to large distances, or large distances to small distances. So you have a circle, everything that is inside the circle is mapped to whatever is outside the circle. So you have a fundamental, and so that means that you don't have to worry about going to zero radius, because whatever happens zero radius, you can describe it by what happened at higher radius. So there's the self-dual point when r squared is 1/2, that it is that you say from that circle, everything that is inside is mapped to everything that is outside. So we only need to know one of the two regions, outside the circle or inside the circle. And that's totally stringy symmetry. Nothing has been seen like that before, and it may have some implications. One of the implications presented that using a symmetry like this is people used to prove that all the different theories are the same. Okay, you can generalize instead of having a circle, you can have a torus, which is a two-dimensional circle. That's a more complicated object. Also, you can have strings winding around the torus. It's nicer to describe mathematically because it can be described in terms of complex numbers. And then you can start putting all the mathematical formalism in terms of Hodge numbers and so on that they're topologically non-trivial. And then you can see that the duality being more manifest. And I'm sorry, I better jump into this because it will be too much detail. And then you can have more complicated objects. The most complicated one is what is called Calabi-Yaos. Calabi-Yau manifolds are the ones that we want to have because when you go we want them to have 6 dimensions because to go from 10 to 4, an object which are 6-dimensional object. And that's an object that admits the Ricci flat metric. That means that the Ricci tensor is 0. The Ricci tensor can be 0 without the whole curvature being 0. So that means these manifolds are very complicated, but being the Ricci tensor 0 satisfies the Einstein's equation very well, and actually is a condition to get supersymmetry. And we want to be in 4 dimensions to get supersymmetry to have a better control on your calculations and probably these realistic issues of supersymmetry. I will leave the slides there, and people who like mathematics, this is a way of enjoying a lot of mathematics in coming from string theory. Actually, there are many examples of Calabi-Yaos. And then one of the things that people wrote a classification of a very large class of Calabi-Yaos and realized that there is this beautiful symmetry where you could plot two of these Hodge numbers. There's a symmetry around this axis, this state and equal to that. That was called mirror symmetry. And mathematicians who had been studying these manifolds, they didn't know anything about mirror symmetry, and it was discovered by the string theorists. Now it's a whole area of mathematics for the last 20 years or so, just dedicated to mirror symmetry because of this. So this is a spin-off of string theory, that contribution to mathematics. Well, we have many challenges. Want to find a realistic model of coming from string theory. We need to get the gauge and matter structure of the standard model, SU3 cross 2 cross 1, and the fermions and quarks and so on. We have to explain the hierarchy of masses. We have to get all the issues about different generations and so on. Hopefully unification. Explain why the proton is stable by Genesis. Get all the beautiful things on cosmology, dark matter, explore dark energy, dark radiation, and so on. So there are many things that we have to put on the list to get something realistic before we can get a realistic model from string theory. Contrary to any model building people do, if any of these things fails, then you have to throw out the model. So that's more challenging than model building that people have been doing in the past. So these Calabi-Yau spaces, you can also have brains that I told you that the brains, and our universe can be one of these brains. And so that's why we see only one point. We don't see all the extra dimensions. We are just sitting in this smaller dimensional object, which is a deep brain. People have been using new tools, and there's something you want to see what is going on in the moment. Using machine learning and genetic algorithms, people have been able to produce more models and to compute the metric on these spaces, which are usually people didn't know in the past. It's something that only happened in the last 5 years or so. And so there's a lot of interest into this more computational aspects, just to understand better this complexifications and to get something realistic. People have found a lot of models. The MSSM, the standard model, supersymmetric standard model, 10 to the 15 or 10 to the 23 from different setups, models which are very close to the standard model. So that's progress because they're essentially very, very close to get what we have been observing in nature. However, there is this big problem, which is modular stabilization. And I will spend a couple of minutes on that. So look at typical Calabi-Yau. you have in the same way that the torus have different non-trivial cycles. Here, this can be have non-trivial cycles but a different dimensionality. This object is 6-dimensional, so this cycle can be 4-dimensional. This can be 3-dimensional, and they have many of these fields called moduli that we have to specify, but at the sizes of each of these cycles. Not only the size of the whole Calavillado, but the size of each of these cycles. And so a way to understand that is that let's consider the metric. The metric, as we know, is a matrix with two indices. And this capital M and N go from 0 to 9. These are the 10-dimensional indices. So you can split it into a 4-dimensional piece and a 6-dimensional piece and the off-diagonal pieces. The 4-dimensional piece is the metric that would give you gravity in 4 dimensions. So that's okay. These indices mu and nu are space-time indices in 4 dimensions. But the ones in the extra dimensions, the indices are M and N. They have nothing to do with our space-time indices because those are the extra ones. So for us in 4 dimensions, we'd see these objects as scalars, objects without any index. Okay, only that there are many of them because you have the M and N tells you how many of them. The same way that these objects have the index mu will be a space-time and the index n will be different. So this will be vectors. We will have only one space-time index. Okay. So the moduli are these guys, the guys who are coming from the extra dimensional component of the metric. So they are attached, they're related to the graviton in 4 dimensions because they come from the same graviton in 10 dimensions. But from our point of view, from our world in 4 dimensions, we'll see them as scalars. And in the same way that the graviton is massless, the natural compactification will give you these objects are also massless. And being massless is like having a scalar field with a potential which is totally flat. So, and that means that it can take any value. So there's no minimum of the potential. So that's why it says that the moduli these are moduli and they're not stabilized because they can take any value. So what we need to do is to generate the potential for these fields. And there's sources of potentials, fluxes like magnetic fluxes and having branes on different dimensionalities and so on. And people can compute the sources of potentials, combine them, and then find a potential minimum of them. And this brings me to what people call the Dine-Saber problem, because this is general property. So you have this feels, just to put in your mind, the simplest case is that this modulus can be this overall size of the whole 6-dimensional object. So the infinite volume is a solution because that will give you your theory in 10 dimensions, which is string theory is consistent in 10 dimensions. So that's a solution, so the minimum can be there. And but then you want to have a scalar potential for that, they will start going up, and then naturally will continue up. So it will be a runaway potential. This is what people call runaway potential. What we want actually is to have a minimum. You want something like this to have a minimum. But in a regime where we can do calculations in which the volume is large but not infinite. But it has been complicated to get a minimum like this because you have to trust your calculations and you have to trust your expansions and so on. So you need it to be in this region and not in that region. And so that's why it's called the Dine-Saber problem. So and once we have had a minimum like this, then it will be very nice because this will give you the value, the potential at the minimum will give you what is called the cosmological constant that I mentioned before. And in being positive, that means that you have a de Sitter, space, time, and being positive, that means that the universe will be accelerating and will explain the current acceleration of the universe. But of course, it has to be positive and very small, and that's the challenge. So people turning fluxes on these different non-trivial cycles, people have been able to find solutions where when you put fluxes in one cycle, then you prevent the cycle from getting big, and then that's a way of stabilizing it. And there are several scenarios that people have having fluxes and branes and so on. At the end, you get solutions which are a minimum that's like the one I was showing you there. So that's progress because extra dimensions people have been talking about since the 1920s as Cadusa climbing. Forget about strings, just extra dimensions. And people say, why is it that we don't see the extra dimension? So that was the answer. The answer is, because they're too small to be observed, as we cannot explore distances very small. So that was the answer. But then the question is, why are they so small? We have to explain. So, and this is in the 20th century, people say we don't know. That let's assume that they're small, but we don't know. Now we can say we have all this complication of fluxes and so on that people have been doing real calculations in the last 20 years. Now we can see that you can fix the moduli, and you can find the volume, and the volume to be very small. Small in the sense that is smaller than the smallest distance we can explore experimentally. And the smallest distance we can explore experimentally is the one that is explored by the LHC in CERN, which are the big colliders. Big energy means small distances, and the small distance is 10 to the minus 18 meters or so. And so as long as this volume is smaller than 10 to the minus 18 meters, nobody could observe it. And that people have achieved in the last 20 years. So that's a real achievement. But gives something more, because there are many of these fields, and there are many fluxes you can turn. The fluxes have to be quantized, and there are many potential values of this minima, of these integers. And so you can see it as a cartoon, a potential with a huge number of minima. For each one, you have different fluxes and so on. And then you have many minima you can have because of quantum mechanics. You can tunnel from one to the other one and then populates. In many of these minima, the cosmological constants of the minimum will be very large, but in other one will be smaller. And then at some point, since you have so many means 10 to the thousands or so, then you can dream to find one that is very small, the 10 to the minus 123 problem that I told you before. And that's what is called the Buzov-Brzezinski approach to explain. So you have all these integers given by the fluxes, and at some point, wherever you are, you can always find a small width of a circle with a small width where you can touch some of the minima. And you want another value of the cosmological constant, but make another circle, and you can always find something in that circle, and then that addresses the cosmological constant problem. And this is something is worth explaining because this is a very important result, even though most of us don't like it. And it has part of a big history. In the 1980s, Weinberg again say, well, what is the value that the cosmological constant has to have such that we haven't observed it, but that the explanation can be that big anthropic in the sense that if we would take different values, we would not be here. And he came out with the value 10 to the minus 120. Cannot be bigger or smaller. It's that value. Okay, so if it will be bigger, the universe will be expanding so fast, and the galaxy will not be able to exist. If it will be smaller, it will contract very fast, and we will not be able to exist. And then Buzov-Brzezinski came out with a proposal of the fluxes that I mentioned before, in the 2000. And the explicit realizations with string theory with modular stabilization, so it came after 2003, when we were mostly KKLT from Carlos Lindy and Trivedi in 2003, and many of us have been working on that for the last 20 years. And the interesting thing is that in the middle of here, in 1998, people discovered the 10 to the minus 120, the acceleration that corresponds to 10 to the minus 120. That means that what Weinberg did was a prediction that was confirmed 10 years later. And this is what I like to call the worst solution to the dark energy problem, with the exception of fault dilemmas, because I don't like it. Most people don't like it, but some people claim that they have another solution, but there are no solutions, because this one has to address all the corrections that I told you are already addressed here. So this is the concrete explicit solution of the cosmological constant, but you need to use this anthropic word that we don't like. So that's the okay. And then you can have predictions, even though you have so many minima. There's a general claim that whatever you do, you go from one minimum to another one, you have a bubble, and the bubble has to be an open universe, and we have to check if the universe is open or not. Also, the string theory can give predictions of which are not so general, but particular models. Some people have come up with models of a string inflation, and so that means to explain the the early parts of the universe with concrete numbers that you can predict, NS and R, and they have been observed. I mean, constrained by the experiments to be less than 0.036 and NS to be almost 0.965. And there are string models that predict values very close to those. Some of them have been ruled out, like this one is too small to satisfy this, or maybe this one to be this too big to satisfy this. And so this is a much more humble approach to getting something predictable from string theory. Just some class of models where you pick who will be your particle when you do the inflation, and then explore that. And there are only a dozen or so models that can be tested, so something is a good thing. One of them that I cannot avoid to mention is because it has a very interesting history, because it's something I worked together with Mahbub many years ago, and now I'm working with with Ahmed on that precisely. So it's my connection with Bangladesh in that sense. Is brain anti-brain inflation. You have a brain here and an anti-brain here and a brain moving. Anti-brain is like this equivalent of antiparticles for the particle, and then they attract each other like a Coulomb interaction, and then when you go there, you can produce this inflationary universe that can be tested experimentally. But after inflation, there are physics that comes fields oscillating around the minimum, can give you a history of the universe which is different from the standard one and can be eventually give rise to some predictability. You can have candidates for dark matter also from what people call dark radiation. I can mention what it is if you ask me. I try to finish now because I can see one thing that I would like to also mention is that many of these initiatives scenarios give rise to gravitational waves of very high frequencies. Now there's a trend to eventually to start searching for them in a systematic way, because the experiments we know gravitational waves are for kilohertz down. This will be preferred to be megahertz or gigahertz or so. So this is a challenge or a possibility for the future that we can see that where gravitational waves coming from string theory can be testable. And I have no time to mention, but there are something called the Swampland conjectures. I will skip and conclude. So as I said, that the string construction get closer and closer to the standard model, to something realistic, the standard model and beyond, but not totally quite, because you have to combine all the standard model things with model stabilizations to get the sitter and to get the cosmological constant to work. Concrete models that to achieve everything is not yet in the market, so that's a challenge. There are general predictions like the existence of gravity, gauge fields, non-continuous spin representation. Sorry, there's a typo. No tachyons, the general landscape. Some predictive scenarios like inflation. Also, you can talk about supersymmetric models, to what kind of a scale of supersymmetry breaking is, and so on. And for the future, we depend a lot on potential observations. Gravitational waves look for me like the most model independent possibility, probably in the very long term, but not necessarily. Actions, which I didn't mention, could be a possibility, like it's very generic in string theory. But there are many open questions. And one particular one is to make sure that we can actually get the Sitter space of the cosmological constant positive from string theory. That's one of the questions that I think is worth. I mean, it's a big claim when we say that we get it, so it needs a big evidence. So we have to accumulate more and more evidence about this. And with this, I finish, and I'm sorry for taking so much time.
Thank you so much for the very nice talk. So